So in the Fiat-Shamir protocol, I have, similar to any other zero knowledge proof, I have the prover and I have the verifier. And the prover would like to, the prover knows W square, W such that W square is equal to X mod N. And so this W is, this X is public, N is also public, but W itself is private. And the prover would like to convince the verifier that it knows the square root of X. So the way the protocol works is that in the initial phase, it sends Y, it picks a random number, and then it squares it, so it sends R square mod N. So this is the commit phase. And then you have a challenge sent from the verifier to the prover. So the challenge is a random bit that is either a 0 or 1. And then the reply to the challenge is Z, and it should be equal to R W to the power B mod N. And then this guy is going to accept if Z square is equal to Y X to the power B mod N. And we said every zero knowledge proof protocol has to satisfy 3 properties. So they call these properties?
Soundness.
Okay, so we have to satisfy the completeness, the soundness, and the zero knowledge property. And we said the first property, which is the completeness, what does it mean? Yeah, but this is how we prove it, left hand. But what does it mean? Like the completeness in words, what does it mean? Okay, so the completeness property, it means that if the prover knows the secret, it should be able to convince the verifier. The verifier should accept at the end. And we said this is the most trivial property to prove, because usually the way we do it is that just to prove that the left-hand side is equal to the right-hand side. And then we said the other property is the soundness property, and we had a technique to prove the soundness property. So what was this technique? So we said we can prove the existence of a knowledge extractor. And how would we run the knowledge extractor? No, you're mixing two things now. Okay, so the noise extract, the way the extractor works is that I run the protocol one time, and then I reset the prover. By resetting the prover, it means that I would force the prover to use the same random number. And then I run it with another challenge. So in here, so this is the extractor. That's a generic technique. It would work for any zero knowledge proof. So the way it works is that you have one run of the protocol. So I have Y here is R squared mod N. And then suppose B here is equal to 0. And then this is the reply. So I'm going to call it Z0. Just to denote that the fact that it was the Z corresponds to the challenge that is equal to 0. So this is R W to the power 0 is equal to 1. So this is R mod N. And then I'm going to reset the prover by this is just a technical term, which means that I'm going to force the prover to reuse the random numbers one more time. And then so the prover is going to send me R square, and then I'm going to challenge him with another challenge. So this is B equal to 1, and then he's going to send Z1 equal to RW. And then simply by dividing Z1 over Z0, I'm going to obtain W, which means that, so W is equal to Z1 over Z0, which means that I can actually use the prover as an oracle to extract the secret key from it. So if I can use you as an oracle to extract some information from you, then you must know this information. So this is a proof of the soundness, and then we have The last property is the zero knowledge property. So the zero knowledge property we prove it by showing that the transcript of the simulator that the verifier can run by himself is indistinguishable from the transcript of the actual protocol. And again, the technique was very simple. The way that guy is going to cheat, or the way we're going to use the simulator is that we're going to pick the challenge first, and if I pick that challenge, then I can construct. If I can construct. I pick that challenge. Once I know the challenge, I can always construct Y to satisfy this equation. So the way it works is that so for the simulator, I'm going to pick B, and then calculate Y equals to something that would satisfy this equation. So it's equal to Z squared. So I'm going to pick B and Z actually. And then I'm going to calculate Y equals to Z squared over X to the power B. And then I'm going to produce the transcript that is X and N, and then Y, B, Z. And then I can just keep repeating this. So I'm going to, and if you observe a sequence that is produced by the simulator, you cannot distinguish it from a sequence like the transcript that was produced by the actual protocol. Any questions on?
This is like a complex problem. How can you force approval and the same random?
I'm not forcing it.
How do you do that?
No, the way I'm saying this is again. Suppose I am trying to convince you that he knows some information, right? So if I can use him if I'm going to interact with him, and if I can, at the end of my interaction with him, and I can interact with him with the way I like, but at the end of my interaction with him, I can tell you that secret. And initially I started without knowing it. Then you should be convinced that he really knows the secret, right? So I set the rules of my interaction with him. The fact that I'm able to reset him did not give him any extra knowledge. Yeah, but again, that fact that I'm resetting the prover did not give him any extra knowledge, right? So this is a very generic technique actually in computer science. If I suppose I have an algorithm that does something, I can just use it as an oracle to get something else out of it. And in my interaction with it, I am free to control that oracle the way I like. So in our case, it's very clear that by resetting this guy, I did not provide him with any extra knowledge. So this did not interfere with the fact that if I am, again, I set the rule the way I like, so I'm able to reset it. I'm not interacting with the actual prover in the actual protocol. I'm just treating it as an oracle. But the fact that I'm able to reset it to reuse the same random numbers did not supply him with any extra knowledge. Right? So it doesn't, I mean, if it would have supplied him with some extra knowledge, maybe if I am sending him this specific random number, you can argue that even with this case, since I don't know the secret I'm starting with, it just doesn't give him any extra information. But we are not doing it in real life. You're saying that we are actually going to reset the prover. I'm just saying that for this protocol, if the prover is acting this way, then I can imagine that I can imagine the prover as an oracle, and I'm just interacting with this oracle, and I have all the ways to set the rules of interaction with this orbital. So in my case, I'm only assuming that I'm resetting the random number within this orbital. And resetting it did not provide the prover with any extra information.
Sorry. You choose B from a two-member set.
Say that again?
You choose B from a two-member set. Is it a fixed set?
Yeah, it's always like that. For this protocol, it's either always 0 or 1. And in the actual protocol runs, every time we run the protocol, like it's a multiple rounds, right? So every time, this guy is going to pick a different random number, and this guy is going to pick B at random. So we have another protocol. The way I'm actually, if I were to ask you any question that relates to zero knowledge proofs in the exam, I'm going to give you a protocol, right? Maybe one of the protocols we studied, maybe it's a new one, but do not memorize these ones. Like, if I were to ask you any question that relates to this protocol, I will give you the protocol description. And then I'm going to, I don't have any tricks. I'm just going to ask you one of the questions that relates to one of these three properties. So to have it as an exercise, let's take this one. Suppose this is an exam question. So this one, I'm just going to give it a name because it's a very famous one. So this is Schnorr's identification protocol. And it's also a zero knowledge proof of discrete log. So if you like to prove to someone that you know the discrete log of some element in a group, or just knowing the discrete log, then you can use this protocol. So here I have public parameters, a prime number and a number g that is between 1 and p minus 1. And then the prover knows a secret s, and the public key of the prover, you can think of the public value is g to the power s. So s is secret and v is public. And the prover would like to convince the verifier that it knows s. So basically it would like to prove to the verifier that it knows the discrete log of v. We know that solving the discrete log problem is a hard problem, but for now, this is a public thing. We know that if I give you v, you cannot find s if you have limitations on your computational power. This is the same basic principles behind the Diffie-Hellman and the Gamal encryption scheme, the Gamal signature scheme, and all these. So the way the protocol works is that this guy is going to commit x equal to g to the power r is just a random number. And then this guy is going to send the challenge e, and then he's going to reply by y equals r minus se mod. Just remember this one because anything that happens in the exponent, it should be modulo modulo p minus 1. If you recall from 6110, when you're doing computation, modulo n, everything that happens in the exponent is modulo phi n. Similarly, if I'm doing computation modulo b, anything that was happening in the exponent would be modulo p minus 1. This is from Fermat-Little theorem or like Euler's theorem. If you don't recall this, just remember it now that for the exponent, when you're doing modular arithmetic, the computation should be done, if you're doing arithmetic modulo p, the computation in the exponent should be modulo p minus 1. And this side is going to accept if x is equal to g to the power y, v to the power e mod p. So I can just think of this as an exam question and try to solve the following questions with me. Just grab a paper and try to prove the correctness of this protocol. How can I prove the correctness of this protocol?
Three properties. We go to
Correctness. I'm only talking about correctness. So how can I prove it, the correctness?
Left equals right.
Yeah, so all I have to prove is that the left-hand side is equal to the right-hand side. And this is a property that we said this is a trivial property to prove.
it's completeness. You mentioned that that's completeness.
Completeness?
Yes.
Yeah.
Completeness, correctness is the same thing. Synonyms.
I should have said complete. Okay. Right.
Completeness,
So,
soundness,
and the zero knowledge. So how can I prove the first property?
we replace y with the vector, we increase the x value.
Yeah, so I just say that the right-hand side. Okay, so to prove the completeness, so the right-hand side of the verification equation is that g to the power y, v to the power e is equal to g to the power y is what? From the description of the protocol. R minus SE, and then v to the power e, v is, from the description of the protocol, is g to the power s. And then this is going to cancel this. So I'm going to get g to the power r, and this is equal to x, which is equal to the left-hand side. All right, can you prove the soundness? Or can you show the existence of extractor?
We take two values of e,
Okay.
and we switch the formula for x for the two values. And x is the same for kids.
Okay. So I have, this is one run, right? I have one run x equal g to the power r. I'm assuming that you're going to write this is mod b, and the other one you're going to put it. And this is e1, and this is the reply is y1 equals r minus se1, mod p minus 1. So this is mod p minus 1. So this is one run. Right? What is the other run? How can I construct the other run? Same, except that I'm going to supply a different challenge. So here the challenge belongs to the so it's not a 0 and 1. It's you have more choices for the challenge. So here I'm going to send the same x because I reset this guy, so it's going to use the same r. I'm going to challenge it by e2, then he's going to reply by y2 equals r minus se2 mod p minus 1. Okay, how would I extract the secret? Where is my secret to start with? S is the secret, right? So how would I extract the secret from what I see or what I obtain from the extract? This part will not give me any information actually. So I can just look at y1 and y2, and let us see what I would get by subtracting them. So suppose I subtracted y1 from y2, so I have y2 minus y1 is equal to what?
R will cancel.
R would cancel, and then I would get
2s.
SE1
Oh yeah.
minus S.
E2.
So how would I get S?
Oh.
So S would be
S.
y2 minus y1 multiplied by E1 minus E2 inverse mod P minus 1. So it's again like very simple algebra would prove to you that I can use the prover as extractor to extract the value of the sequence. What about the third property or the zero knowledge property? How would I construct a simulator? Usually, the way I construct the simulator, look at what the verification step, and this will give you the clues to how you would construct the simulator. Again, whatever I'm saying is generic. You can apply to all the zero knowledge.
I choose X.
If you start by choosing X, you are somehow stuck.
Sorry, choose Y first.
So choose Y or E, or both.
Choose Y.
I can just choose both of them, right? I choose Y and E, and then I calculate X. So the simulator is as simple as pick Y, pick E, calculate X equal to this, produce a transcript that is X, comma Y, comma. You can put the public parameters also in the transcript G and P as well. So again, the way the simulator works is that this is the way you cheat, right? If you know a priori the challenge, you are able to cheat. So you pick Y, you pick E. If you pick this and this, you can calculate this. And then you can produce these three triplets. Or you can produce this triplet, X, E, Y. That would satisfy this equation. Any questions on how the simulator is constructed?
Can you repeat the last one?
Okay, so the simulator the way it works is that you pick Y and E at random, pick random Y, random E, and then calculate X equals GY VE mod P. Right? And then the transcript will be this XEY triplet. This is output, you can just cite output. This triplet. You can look into the slides where I am writing it in a nicer way than the way I'm writing it on the board. Any questions?
The previous slide, when we are on Fiat Shamir in parallel, how is it not zero? There is no zero knowledge.
In the parallel version, I told you about two parallel versions, right? And in the Fiat Shamir, let me actually have the slide so that I don't draw it again. It's set 4, right? No? It's 3. 4 or 3? Okay, I don't have. Okay. Anyway, in this version we said I instead of having multiple rounds, I could just do one round where I am sending in the Fiat Shamir. One round worked like this. I sent R squared mod n, and then the challenge was B, and then I was sending RW to the power B, right? So if I would like, I don't have to do like if I don't have to. So this is one round, but it doesn't give me enough confidence that this guy is not cheating. Because he can still cheat with probability 50%. So if I like to get more confidence that he's not cheating, I'm going to repeat it. Suppose this is R1 and this is R1 and this is B1, B1, right? So I'm going to repeat again with another round where he's going to pick a different random number. I'm going to send a different challenge. Then he is going to reply by R2WB to the power B2. Then I can just do it for T times, right? The thing is, I don't really need to do this and then this and then this and then this. I can just have one round where this guy is going to send me R1 square, comma, R2 square, comma, R3 square, comma.
At the same time.
At the same time, I'm going to send him all the challenges at the same time. He's going to reply back with all the replies at the same time, right? For this version, I still can construct a simulator and I have the zero knowledge property. So again, I can have a version like this that is going to work like R1, R2 square up to RT. So I have T rounds square. And then I'm going to get challenge B1, B2 up to BT. And then I'm going to reply back by, let me just call this one Z1. This is Z2. I'm going to reply back by Z1, Z2, and they are constructed this way, up to Z3. Okay? For this one, they satisfy the three properties. But still, I have three messages going back and forth. Suppose I just would like to get it in one shot. I would like that prover to send one message that just finishes the whole protocol. So I would like to send, to emulate or simulate the case that as if I am receiving the challenges, right? So this guy, the way I'm going to do it is that
Using hash.
I would like this guy to send me something to prove that he picked this one. Again, if the prover was able to pick this at the beginning, he can always cheat. Right? So this is the problem I'm trying to solve. I wanted this guy to send something, send R and something that also he has no control on it. So the way it's going to work is that he can send me these. In your slides, I'm calling this Y1, Y2, up to YT. Okay? And then we're going to hash these. And we're going to take the first T bits of this hash. I'm going to treat them as beans. So in this case, it's going to be one message, right, where he's going to send Y1, Y2 up to YT. And these beans, but they are not coming from that side. These beans are produced by hashing this and taking the first T bits. So he has no control on beans. Right? So he cannot bake them and then go back and bake Y. It should be done. I'm forcing it because of the one-witness property of the hash function. I am forcing it to do it in order. So now, this is the beans constructed by hashing this and where this one is h of say y, and let me just say that first t bits of hy, and then this is the z's. So now this protocol does not, I cannot construct a simulator for it. Because if you try to do the simulator, the one-witness property of the hash function will prevent you from producing the transcript. And that's why it is said in your slide, it says it doesn't satisfy the need. even this proxy, the thing is, the way the protocol is working actually, I don't send anything to the group.
There's no time because we cannot.
Anything that has to do with hash functions, you lose proofs unless there's another model for hash function, which we call the random oracle model, in which we have more assumptions about how the hash function behaves. But if you just say that I'm having a hash function implementation using SHA-3, for example, or SHA-2, I cannot have any formal proof. So it's hash functions are actually very interesting because they are very, very efficient. But you will see that most of the protocols, the fancy ones, are not using them because you cannot have a proof, and people are more inclined to use protocols that have some proof. All right, so the second topic I'm going to cover is commitment schemes. So I'm sure again you must have heard about it in 6.1.10, but we're going to cover it slightly in depth. So a commitment scheme, the best analogy for a commitment scheme, or all the commitments protocol work like this. You have a commit phase. So this is a commit phase where you send your commitment. So it's as if I'm putting a message M inside a box and I'm locking this box by some key. And then in the second phase, which is the reveal phase, I am just revealing the key. Right? So I send the key and then the other party is going to open the box and he's going to see the message. Right? So then again, I would like to force this side. Suppose this is Alice and this is Bob. I like Alice to commit to something, and I don't want Alice to have the freedom to change her mind after she commits. But I don't want Bob to know what Alice committed to until we go back to the second phase, where we call it the reveal phase, where Alice reveals the value she committed. So we have different situations where such a primitive is going to be very useful. You can think of it in like the traditional example is in the bidding. If you have a bidding protocol, for example, and then these guys are sending their bids, and in the initial phase, and then you have, after everyone submits his bid, you have the other phase is the reveal phase where they open their bids. Right? And you don't want the guys to know what values these guys are sending, so it's not Alice only. Right? You have several people committing, sending their closed bid. It's as if they send their values in a sealed envelope. And after the bidding phase or the commitment phase is done, you go back, you open the envelopes. So the way we're opening the envelopes is that we're asking them to review. In the commit phase, we don't want anyone to be able to peek inside it. But we also would like these guys not to be able to change their opinion after the commit phase. Right? So let's talk about one way of doing this. So suppose I'm proposing now, maybe a good way to build a commitment scheme is to use an asymmetric key cipher where I'm going to encrypt the message I'm committing to by under a key K. So this is my commitment. And then so this is the commit phase. In the reveal phase, I'm going to send K. I can send M as well, right?
But nice bit.
I can just send K. So is this good?
No, and
Anyone who reads the channel, they can basically
Anyone who read the channel, which channel?
like basically it can authenticate to the
No, this is the commit phase, right? And this is the reveal phase. So anyone who reads the channel at which phase?
if you have the EK.
Okay, so this is one, right? Okay, anyone who reads this would get what?
nothing.
If they can read the K next in the next iteration. they-
Yeah, but again, like I could have actually sent M in the next iteration. Like in here, it's perfectly fine. I can send M. I don't like. I'm actually by reveal, by definition, I am revealing the message.
What is the goal here?
So the goal here is, okay, let me formalize the goals in here. I'm talking about what we call the hiding and binding. Okay. So the hiding property, I am protecting this guy from that guy. I'm hiding that message. And by the binding property, I'm protecting this guy from this guy by making this guy binded to his original commitment. So the goal is to satisfy both the hiding and binding properties.
So we need to identify the identity of the sender.
Um,
You don't know.
No, doesn't
No,
matter.
like the protocol is as simple as like don't confuse yourself with, just focus on these two properties here, the hiding and binding. And hiding by definition, it means that after the end of the first phase, no one will be able to get any information about the message. Binding, again, after the end of this phase, this guy cannot reveal a different message than the original one he committed to.
The problem is the key shared among the players. It's the same, all the players have the same key to encrypt.
No, but no, it doesn't have to, like here you can pick a different key, like it's not shared.
But the key for the protocol is the same.
No, no, no. If I would try it, I would pick random K. Pick random K.
If Alice commit to the same message again,
This technique is not finding end of sender because you can find another key and another message that will encrypt to the same cycle.
So how would I find another key and another message? That will
For example, if it's like one time that, for
no, no,
example,
just show me by equations for any cipher. How would I do it?
cipher decrypted using different key.
So let me help him. So he's saying that technique doesn't seem to satisfy this problem. So the example is very simple. So this guy is going to commit, so this is C equal to encryption of K with M, right?
Yeah.
Let me just call it K1 and M1. So the commitment is C, right? So he commits by C, he sends C. Now, on the side, he can actually decrypt C by any other K, K2, and he's going to obtain M2. And then in the reveal phase, he can reveal K2 and M2. And still would satisfy the original commitment. And so in the reveal phase, he's going to reveal K2 and M2 that are related by this formula, where M2 is calculated by this. So it means that that side is able to change her opinion. Like after the commit phase, the binding property doesn't hold.
unless include the K within the message.
It doesn't. You mean put something inside?
Yeah, and encapsulated with K.
You don't want to go into this
Confuse
because
yourself.
encrypting the key with the key, like we would like to have a cleaner primitive, I would say.
So yeah, the signature.
Hmm?
Can send like random numbers.
Let's just, I want to make sure that you understand this, why this is not a good solution. Can you repeat the solution? Okay, this is the solution I am suggesting, and in here I'm showing you that it's a bad one by showing you that it doesn't satisfy the binding property. So how would I show you that it doesn't satisfy the binding property? I say that I commit, and in the reveal phase I reveal a different message, but still that side will not be able to tell that I was cheating, because still that I can convince him that
So he doesn't know that, yeah.
he's going to check if that C is equal to the encryption of K2 with M2, and if you put that equation, encryption with K2 of M2 is this, so encryption of decryption of C is going to give you C.
Excuse me, sir. In reveal part, doesn't check the length of the message in here.
But it's still, in this case, suppose I'm using a block cipher, the length of the message will not
Is
change.
this?
When I'm talking about the hiding property and the binding property, I talk about two types of hiding and two types of binding. I talk about computationally hiding, which means that I am being protected against a computationally bounded adversary. So in here, I'm talking about these properties that I am concerned with. I'm concerned with two properties, the hiding property and the binding property. But each one of them is defined in two different senses. One of them is unconditional hiding, unconditional binding, or computational hiding and computational binding. So I talk about unconditional. So every one of these can be either unconditional or the other one is unconditional, the other one is
Condition.
computation. So if I'm saying that this commitment scheme satisfies the unconditional hiding property, it means that no matter how powerful this guy is, he will not be able to reveal any information about M. If it satisfies the computational hiding, it means that if he is computationally bounded, he will not be able to reveal information about M. But if he has no limitation on his computational power, he can reveal M. Same thing for the binding property. If I talk about unconditional binding, it means that this side, no matter how powerful it is, it cannot change its mind. If I talk about computational binding, it means that if it has some limitations on its computational power, then it cannot change its mind. So ideally, which commitment scheme you would like to use?
Unconditional.
Unconditionally hiding and unconditionally binding at the same time. So this is the ideal one. We have a very simple proof that you cannot have a commitment scheme that satisfies both at the same time. If you satisfy one in the unconditional sense, the other one, the best you hope for is to satisfy it in the computational sense. So let me give you a very simple proof for this. But before I go for the proof, do you understand the definitions? Talk about two properties, hiding and binding. I have two players. One is committing and the other guy gets the commitment. So to protect the guy who commits, I like the commitment scheme to satisfy the hiding property. But to protect the guy who is receiving the commitment, I like the commitment scheme to satisfy the binding property. Ideally, I would like both properties to be satisfied to be unconditionally satisfied. I don't want to have any limitations on the assumptions I assume about both parties. But we can have a very simple proof that the best I would hope for is that one property can be satisfied unconditionally, and the other one, the best you would hope for is to be satisfied computationally. So just to convince you with things, like suppose my commitment scheme is just C of a message. Any function C, in general, it should be a function of the message, right? So suppose it says, can I have a deterministic scheme that would satisfy can it be unconditionally hiding? C again, C is like your commitment is C of M. It's a function of M. Right? It cannot be like this is the most general case, right?
Yeah. It's deterministic.
So can it be unconditionally hiding? If my adversary, I'm sitting on that side, right? When I'm talking about the hiding property, you should be protecting the message from me, the person who's sitting on that side. If you talk about the binding, you should be protecting the attacker is in this side. So now I'm talking about the attacker who's sitting in this side and would like to know M. If I use a deterministic scheme like this, can I achieve the unconditional hiding property?
I will do brute force.
I will just do brute force, right? If I do brute force, then I will find M, right? Because you're giving me C of M, I'll just try all possible values. I'm unconditionally bounded adversary. I don't have any bound on my computational power. I can just brute force all M and I will find the M that satisfies this, right?
Yes.
So it means that this will not work. I have to have some randomized scheme. So I'm going to make the general case, it's going to be a function of M and a random number.
Why not? It is infeasible.
And the main idea is that if I find M that makes this, maybe there is another pair of like another. I'm going to have this guy always doubting that he found the right M, because maybe there are going to be, for the same value of CM1, R1 might equal to CM2, R2. So even though I'm very powerful, I can do exhaustive search, I'm not sure, because for every MI I find, there is another MJ that is going with another random variable that will give me the same commitment, right? So this guy is always going to be doubting that he found the right M, right?
Yeah.
But what does it imply is that if there is always M1 and M2, such that M1 is not equal to M2, and R1 and R2, such that C of M1 R1 equals C of M2 R2. This was my condition to achieve the unconditional hiding. But it literally means that if this side is unconditionally, it doesn't have a constraint on its computational power, he can break the binding property. So again, it's your way of achieving unconditional hiding. Your only way to achieve unconditional hiding is to make it
computation.
it cannot be unconditionally binding at the same time, right? So the best you would hope for is that you would make it like computationally binding. So there is, whatever I'm saying, there is no math in this, it's just pure common sense. We're talking about two properties, you have two people interacting with each other, you're trying to protect them. We're just giving them these properties, we're giving them fancy names. The person who commits, you're trying to protect him by designing a commitment scheme that satisfies the hiding the property. The other person, you're trying to protect him by designing a commitment scheme that satisfies the binding the property. And then each one of these properties can be satisfied in either in a computational sense or in an information theoretic sense. If it's satisfied in information theoretic sense, it means that I don't have any assumption about how powerful my adversary is. So we call it unconditional binding or unconditional hiding.
It's very,
Any questions?
just
Right, so you guys can take a break of maybe 5 minutes. While you are in the break, it's not a pure break, you can fill in the schedule for the next lab. One of you emailed me for the, okay. The thing is, I literally